Alright guys, so in the last video we defined the Riemann sum. And let me scroll up a little bit, kind of show what we started talking about. So we defined the Riemann sum in our last video, and we basically said that it is how we approach the definite integral, alright? So remember we said that, hey, if you want to find the area under a curve, you partition as many of these little boxes under here and you add them all up. The adding of them all up is where we get our summation notation. Alright, and then Bernard Riemann was like, well, there's got to be a way to get a stronger approximation, because obviously as you add more rectangles that are in there, then you're going to get closer and closer to the actual value underneath that curve. And so that was represented as n was approaching infinity. And so we wanted to find the limit of, as n approaches infinity, of the summation of whatever the function of the curve actually is. We defined delta x to be the change from b minus a over n, or basically our number of partitions that we are going to take. So let's take a look here at an example. It says find the area under the curve of f of x equals 1/5 x squared between x equals 2 and x equals 6. Okay? So let's just start off this. At some point, what we're going to get to is we're going to get to a spot where we can just simply solve or evaluate this integral here without having to do any Riemann sums, all right? Before we get there, let's use quote-unquote the long way out to kind of see where this all stems from. So we are going to use Riemann sums to instead solve this or evaluate this particular integral here, okay? So this is really the same thing as the limit as n approaches infinity of our summation from k equaling 1 on down to n, okay? And so we're basically kind of taking this and then using our f of x, all right, of f of x multiplied by delta x here. All right, so our answers are going to be left in Riemann sums. All right, our answers are going to be left in Riemann sums here. So let's kind of take a look at what we need first and foremost. Okay, well, first and foremost, let me start changing some colors on that. We need to know what delta x is. Well, delta x is our partitions. All right, what is our partitionings happening here? So in our case, it was b minus a over n. Or we're dealing with 6 minus 2 over n, which in this case is 4 over n. So we're going to have to use that to go back into our Riemann sum summation notation. So we needed to know what delta x was. We also are going to have to know what the x to the k actually is going to be. All right, we have to figure out what x sub k is going to be in this case, because remember, it's changing constantly as you're dealing with your function. All right? And I actually kind of forgot down here, this should be k minus 1 in this particular case. Right? So it's basically saying what x sub k. X sub k is going to be your particular partition that you are dealing with here. All right? And so let's take a look at what we have. All right? So we are starting as x sub k. So x sub k in our case is going to be 2, because that's kind of our starting point at 2. And then we want to know what it is once we change x for, oh, not x, sorry, let me erase this real quick, not k. Alright, we want to know what is happening every time I have my starting point of 2, and then what's going to happen with that change of x for every new k that comes into play, right? So every time you have a new partition, that new k. So I start at 2, that's my starting point of my interval, and then every time I reach a new x sub k, that's going to be when I take 2 plus the change of x, what is my partition right here, my change of x, all right, and multiply it by what that new value for k is, or that new partition that's going to be coming into play, okay? Well, we know the change of x in this case is going to be 4 over n, so this is 2 plus, excuse me, 4 over n times k. So that is my x sub k. Well, think about what happening is. X sub k itself, all right, is going to give you the x value that you are looking for, okay? But in order to find your actual area of each of these partitions, you need to find the area of the rectangles. Well, in order to find the area of the rectangles, you need your base, you need your height. So the height is going to be represented when I find f of whatever x sub k is. All right, so I need to find out what f of x sub k is going to be in this particular case. Well, that is going to be 1 over 5 times x sub k quantity squared. Well, I already have a value for x sub k. That is 1/5 multiplied by 2 plus 4 over n times k quantity squared. All right, so this represents the height of my triangles. So now it's my job to figure out, well, what's the entire area going to be? Well, the area is going to end up looking like our change in x multiplied by our height. Because our change in x, that represents what our base actually is, right? Our change in x is our base of the triangle, or the rectangle, excuse me. All right, so the area, in this case, the delta x was 4 over n, and the height we just said was going to be 1/5 times 2 plus 4 over n times k quantity squared. All right? And so, kind of just simplifying this just a little bit more so, we get 4 over 5 times n, and then 2 plus 4 over n k quantity squared. All right, so as we wrap up this, we want to write this in a Riemann sum. So our Riemann sum is going to be the limit as n approaches infinity of our summation notation from k from 1 to n as n approaches infinity of what we just found for our area. 2 plus 4 times k over n quantity squared, and then we multiply that by our change of x, or our delta x, which was 4 over 5 times n. Okay? So there's a little example as to what we are looking at for our examples of Riemann sums. And on to the next one.